Thank you very much, Clément. So it is, as Clément said, the fourth lectures of this rainy season in Paris, and I hope when I will gone, you will have a much better weather than during this period of lectures. So what I will try to tell you today, in fact, is the last part, as Clément said, when we discuss general aspects of the controlled or living radical polymerization. Then we went through some mechanistic issues, how one can control polymerization under best conditions, how to optimize it for different initiators, different monomers, different targeted systems. Then we discussed about the various aspects of polymeric architectures, branching, topology, sometimes composition, gradients, and gels, networks, and so on. And today I will finish with really giving you some examples about the organic inorganic hybrid material, something which is of a really big interest to a group of Professor Sanchez, but also a little bit about the bioconjugates, about complexes with nucleic acids, about also proteins, how one can make them efficiently, and sometimes what kind of uses they may find. So let me start first with the organic inorganic hybrids, and the general overview essentially is such that you can have a various type of a substrates of a different shape. Typically, it would be nanoparticles of a size from sometimes 5 to maybe micron nearly diameter. It can be sometimes a flat surface, so typically would be a wafer, would be glass or silica, or could be silicon, could be gold, and also cylindrical structures. And you can grow from the surface outside or inside, so it can be convex or concave systems. And of course, what is needed in that case, you need to first functionalize the surface. So in fact, for the silica or for silicon, you have silanal groups on the surface, typically, and then you can convert these silanal groups to something which would contain initiator for atom transfer radical process. So typically would be bromoesters, bromoamides, sometimes some bromonitrile groups, and so on. And then you can carry out polymerization, as we discussed, in a controlled way. You can control also grafting density by essentially controlling the initiation concentration or initiator concentration of the surface. There are some issues which we will be discussing very briefly, how one can prevent termination in these systems, because they are very multifunctional systems, and it will be different issue on a flat surface and also on these nanoparticle surfaces. But if you do it in the right way, you can end up essentially with sometimes very regular structures. They can form Bragg diffraction essentially patterns, so getting photonic type crystals, having them at very high concentrations, sometimes up to 75% by weight of inorganic component, and still having elastic polymer-like properties for processing and some others. So I can start with one good example that you can control these structures quite precisely. For example, if you have a silica particles of diameter around 20 nanometers, so surface area for a sphere will be around 1,000 square nanometers, we can put initiators approximately 1 per square nanometer, and then we can grow 1,000 of these chains from the surface of a silica particle. So if it would be a degree of polymerization, let's say 20,000 of each chain, I have thousands of them, so it would be 20 million, sometimes more, of the object of this quite regular structure. And you could see them by AFM that you have a hard silica core, and then you have a softer acrylate, and longer chains essentially lie on the surface of mica. You can nearly count how many chains you have. You can dissolve this silica or destroy it essentially, or etch it, and in that case with HF you will get the individual chains, and you could see that these chains can be analyzed by a classical gel permeation chromatography, so you can measure what is molecular weight distribution, how many chains you have, what structure you have. And even if it's a living process at the chain end, you have an initiator, you can extend it and make sometimes block copolymers this way. However, there are some challenges, and challenges especially because you have always radical termination. Radicals terminate with rates which are diffusion controlled, and you can, depending on the essentially concentration of radicals, you can predict how many chains would terminate. And termination can have two different consequences. So sometimes termination can be between two radicals on the same surface, so it would be intraparticle, but sometimes maybe also interparticle. An interparticle, if you have 1,000 chains, even if 0.1% of them would terminate between particles, you get a gel. So there is a challenge, how we can prevent it, how we can avoid it if we want to have a really fully soluble systems. So one approach is that we can have under higher dilution, so of course concentration would be lower. We can limit polymerization to lower conversions, have lower molecular weight, have slower reaction, which means less radicals. We can in fact add extra copper-2 at the beginning, because otherwise this termination reaction will lead to the formation of copper-2. It has to be produced in order to control according to persistent radical effect. But sometimes we can really add extra copper-2, so we don't need to sacrifice some of this termination in order to form it. Sometimes we can add even extra chains. They can screen these particles and they will have a less termination. However, other approaches would be based on compartmentalization, essentially using mini emulsion process, but also going to a higher pressure. I would like to tell you also that sometimes it's not obvious that if you have a diameter really the same as a distance separating these walls of two different particles, in fact, in a classical FCC packing, you will get only 6.5 volume% of nanoparticles. And this, of course, means that in a nano composite, the distances would be very, very small, even if you have a loading relatively low, like 6 volume%. And of course, we need to do this functionalization. I mentioned to you about the silica or signal groups. Of course, we'll be using mostly chlorosilane, sometimes alkoxysilane, but for gold or for iron, for cadmium sulfide, for some others, we'll be using different anchoring groups in order to make them efficiently connected. But let me show you one example of a high pressure. I made some similar example during the first lecture, but I think it's a really one way to make a very well-defined polymers. So here, if I go to higher pressure, generally propagation rate coefficients would increase because we have a negative volume of activation, but termination, in fact, will decrease because you will have a higher pressure, higher viscosity, and therefore diffusion control limit will drop from 10 to the power 9, 10 to the power 8, 7, sometimes even 6. So if I go to relatively high pressure, and in that case, 1 kilobar, approximately 1,000 atmospheres, so this is 6 kilobars, 1 kilobar will give you factor of 2 better Kp to Kt ratio. If I go to 6 kilobar, it would be Kp to Kt ratio larger by factor of 100. So termination or proportion of terminated chains will be 100 by 100 times lower, so 10,000 times. So under these conditions, really you can forget about the termination, and you could see that I can grow methyl methacrylate, even at room temperature, to molar masses of individual chains being over 1 million. And these chains are still active, so I can extend them, for example, with methyl acrylate, and I get individual chains 2 million each, and thousands of them, roughly speaking, on the surface. So why we try to go to this really analysis and understanding of different composites? Because they behave in a very special way. If you look here, what happens if I start with silica? These are 20 nanometers diameter. Degree of polymerization of styrene 10, 150, 700, 1300. And the same would be similar for methyl methacrylate. If I plot the dependence of the degree of polymerization of chains coming from a surface versus distance separating one particle to another, you have like two different regimes. One gives you the first regime, it's a concentrated polymer brush regime with an exponent 0.8. So 0.8 is really, if you would have a 1, they would be perfectly stretched. So they are nearly perfectly stretched, very strongly elongated. But at a certain moment, you start seeing that this value 0.8 changes to 0.5. And you go from concentrated polymer brush regime to semi-dilute polymer brush regime. And they have a very different mechanical properties. Because here, these chains are highly stretched. They cannot entangle. And because of that, they will have a very poor mechanical properties. If you go to this semi-dilute polymer brush regime, now they would start behaving like polymeric materials. So you could see here what happens if you would take a very thin film, essentially monolayer film. If I have a degree of polymerization 10, everything breaks. If I go to degree of polymerization 150, you start seeing nearly a behavior like crazing. So these chains start entangled and mechanically were enforced. If you go to 760, now you have this perfect crazing. They behave like a really high molecular weight polymers, and you could see even on the next slide some magnification that you can trap these silica particles in this craze formation process. So macroscopically, they also behave very differently. So this with degree of polymerization 10 essentially is like a sand. There is no really cohesive forces joining them together. The P150, they still break, but 770, you could see it's a polystyrene, in fact, 99% polystyrene, but instead of being brittle, you can essentially roll it, you can bend it, and it behaves in a much better way. So what happens here, there are really two phenomena. If I have a very short chains, in that case, this semi-dilute polymer brush would be below this critical entanglement molecular weight. In that case, you have a brittle fraction. But if I go now to this critical value above a semi-dilute polymer brush regime, above this critical value, now you start getting this crazing behavior. And for polystyrene, this value is around 180, which means if I go to this semi-dilute polymer brush regime above 300, in that case, they have a mechanically much better properties. However, sometimes it comes at a certain expense. So if I would go to the really high and higher molecular weight, I will have a tougher and tougher material, but also I will lose some order, because now if you have a very long chains, they cannot be registered if I would like to have, for example, photonic material. So there would be some kind of a transition, and this transition, in fact, depends on at least 3 parameters. So one parameter is a curvature of a particle. If I would go to larger and larger particle, they are flatter and flatter and flatter. I need to go to higher and higher molecular weight in order to go to this tougher material. The second issue would be graft density. I can reduce graft density by making them less dense, and in that case, they can entangle much easier. So you could see that if I reduce graft density, in that case, I can cross from one to another regime at a lower molecular weight. So in principle, you can do that, but also if you go to high and higher molecular weight, instead of having ordered structure, you get a disorder. But in fact, there is a borderline regime in which you can have both of them together. So here is a relatively narrow regime that you can have both ordered structure and tough structure, which means you have a mechanically very sound materials. So here are some examples of that. So you could see that if I go, this is a little bit larger silica particles, they are in a range of 120 nanometers or 200 nanometers. You could see that going to this value of the polystyrene 700 and 2000, they are very, very nicely ordered. And in fact, here they are so strong that you can have typical behavior for polystyrene, but also these photonic-like materials, because you have this refraction between the 2 different refractive index materials, silica and polystyrene, and you can bend them, you can stretch them, so they are very good materials as potential photonic paints or photonic inks. So another question is how much you can put these silica particles in a matrix, and can they be very nicely dispersed, reinforcing them? And in fact, if you start with the same type of polymer, so this is an example of polymethyl methacrylate grafted from a silica, degree of polymerization 40, and I use a matrix of degree of polymerization 10,000, or let's say 1 million molecular weight. So you could think that they are really same PMMA, but they very strongly aggregate. And this is to a fact that you have a depletion of mixing, and in fact, this matrix, in order to wet this brush, must be of a molecular weight smaller than the brush. And if I have a molecular weight here, 1 or 10,000 or 1 million molecular weight, it means I would need also to have a very high molecular weight brush, which I can do by high pressure, but this is really not that convenient to do. So can I solve this problem somehow? Can I still have a nicely dispersed short chains from a silica particles? You need, in that case, to have an enthalpy component favoring that, because entropy here is against you. So enthalpy means that you should have exothermic mixing. And there are very few examples of polymers which mix. One example, in fact, is polymethyl methacrylate with styrene acrylonitrile at certain composition of acrylonitrile. And this is negative value of the enthalpic of free energy component, and in that case, you can really disperse them evenly. So here is degree of polymerization, styrene acrylonitrile, only 17, and matrix is 1 million molecular weight, and you could see they are very evenly dispersed. So now, can I do the same with one component system? So with one component system, if I would have a very short chains, in that case, there would be very poor mechanical properties. If I would have a very high molecular weight, you would have a low loading. So can I combine these two things together? And the idea is really to grow with a bimodal molecular weight distribution, but what you see here is really how much I can put this styrene acrylonitrile brush with PMMA of high molecular weight. Volume percent, 50%, so by weight would be 75% of a silica, and you could see they still have very good mechanical properties, good transparency, and you can stretch them like polymeric materials. So this bimodal stuff, which I mentioned to you, is relatively easy to do because you can start growing chains, all of them. At a certain moment, you quench them. For example, in a radical process, you can add nitroxide, and some of these chains would stop growing, some others would continue to grow. You can isolate them. You could see exactly what would be this bimodal type of molecular weight distribution. So for example, if I have a 63% of inorganic materials, very short polystyrene, degree of polymerization 30 or so, you could see that they would really crack. There is no really mechanical integrity for this sample. If I go to bimodal distribution, I have degree of polymerization 10 and 130. It is 67%, and you start seeing already some kind of entanglement. Another option would be to go to longer polymer chains, but this is below this critical entanglement molecular weight. You could see they break. If I go, here is 20% inorganic, this is 21, and this is bimodal distribution 50-600. They have this crazing behavior as I showed you before. So this is really one possibility how you can control loading and mechanical properties. Now, something which we discussed with Professor Sanchez several years ago is can you grow efficiently polymers from inorganic surfaces if you have a limited or confinement nearly regime. So if one would start from mesoporous silica, these are SBA 15 with 10 nanometers diameter holes or cylindrical structure, we can put, using chlorosilane chemistry, these bromo initiators, and then start growing polymer chains. We did that for different materials, and in fact, when you think about it, can you grow polymer chains in such a confined space, only 10 nanometers? Can you have activation, deactivation? Can you have a growth of these polymer chains? Can they uniformly grow at the same time? Plus, for polyacrylonitrile is also, as you will see later, a challenge because of solubility. And apparently you can do that, and you can grow with polyacrylonitrile, then you can carbonize or graphitize them, remove silica, and observe essentially these carbon nanorods. So here is a result. You could see that indeed you can have this very well, nicely ordered structure because you have some holes in these mesoporous structures and they somehow keep them together. Surface area is in a range of 800 square meters per gram, very large pore size volume and very uniform pore size distribution. Typically, if you start looking how polymer chains grow from a flat surface, it's very difficult because the amount of a polymer which you can harvest is minimal. If you have a 1 by 1 centimeter wafer and you have a 1 micron thick film, you will get only absolute value would be 1 microgram of a polymer, so not enough to analyze it by GPC. But if you have so large surface area, like 800 square meters per gram, essentially you can harvest the polymer and you can see how these polymer chains would grow progressively during this process. So you can follow pore size, which would be progressively smaller and smaller and smaller. You can look at the total amount of a polymer by TGA. And if you look at GPC, in fact, it's very interesting because you have extremely narrow molecular weight distribution. These values are in a range of 1.07, 1.06, 1.12. So all of these chains grow concurrently in this confined space with a very high precision. But at a certain moment, they stop growing essentially, this peak doesn't shift anymore, and you start getting a kind of a shoulder, higher molecular weight shoulder. So really what happens, of course, you have not only surface inside but also outside this mesoporous structure. So because they have a very similar narrow molecular weight distribution at the beginning, it indicates that they grow at the same rate, inside and outside. But then once you fill this polymer inside, they can only grow outside, and these apparently start growing in a way which would be concurrent at the beginning but continue to grow later. So this brings me really to idea how you can use templated process. We are interested in nanocarbons, carbons which are nitrogen doped essentially, carbons, and there are two ways how to do that. One would be to apply hard templates, and this was one example which I showed you before, using this mesoporous silica. But you could do exactly the same with silica particles, and then you can graphitize them, etch them, and then you have a membranes which would be filled with many pores which are replicas of these silica particles, whether it would be 15 nanometers, 20, 30. You can dial, you can have also bimodal distribution, if you wish, of these silica particles. Another approach would be based on a really soft templating process. So in that case, we'll be using block copolymers, and I will tell you a little bit how one can control this polyacrylonitrile, what to do with it, and how various applications will be related to electrochemical properties or CO2 captures or supercapacitors and some others. So let me show you first how this is done with these silica particles, following exactly the same procedure as before. We functionalize surface, and then we grow polyacrylonitrile. Then they are carbonized under conditions which I will explain on the next slide, and then they are etched and give you these porous materials with a surface area approaching 500 square meters per gram and relatively narrow pore size distribution, which we can really control depending on the size of these particles. So soft templating is probably a little bit more easy for polymer chemists who are not organic, inorganic hybrid people. So we start with a block copolymer of polyacrylonitrile and typically sacrificial block. So in this particular case is polybutyl acrylate. They do not mix together, so they would phase separate, depending on, of course, volume fraction, but also to some degree on molecular weight distribution, because as I explained last time, dispersity may affect also morphology in some sense. So we phase separate them, and you can have a classical spheres, cylinders, bicontinuous, lamellar structure, and inverted structures as well. Then what happens, you will have a two-phase system until you reach order-disorder transition temperature. For this case, it would be around maybe 300 degrees. So I need to fix morphology at lower temperature, and this is done by cross-linking of polyacrylonitrile. I will explain on the next slide how it occurs, but this is something which spontaneously fixes this morphology, and it cannot go through order-disorder transition temperature. Because of that, we will have really possibility of developing this structure. So at low temperature, they are phase separated. At higher temperature, we can have only this residue of a carbon, because polybutyl acrylate will disappear as a sacrificial block at around 450 degrees. So polyacrylonitrile. Polyacrylonitrile is a kind of a special polymer. It has pretty high thermal stability until it starts cross-linking. It has a very good tensile strength and modulus. It, in fact, before melting, it degrades, but also has a very poor solubility. In fact, it's one of the few examples of polymers which are not soluble in their own monomers. So polyacrylonitrile is not soluble in acrylonitrile. You need another polar solvents. I will show you some examples, DMF, DMSO, and some fancy also systems as well. Polyacrylonitrile is used to make carbon fibers already for maybe 30, 40 years. Also acrylic fibers, which are copolymers with a little bit of acrylate. for coatings, for filtration membranes. You can also, by modification of polyacrylonitrile, sequestrate heavy metals. You can remove uranium and some other metals as well. So special thing of polyacrylonitrile, in fact, is that it can be stabilized or graphitized, if you wish, by two different processes. One would be cyclization, so it is formation of a leather-like structure. And the other one is dehydrogenation, so it would form conjugated structure. In fact, you start seeing color develop, and this color is partially due to this conjugated structure. And eventually, you can have at this stage dehydrogenation or at this stage cyclization in the presence of a little bit of the oxygen. It can be just air. In fact, at around 220 to 280 degrees, it forms this cross-link structure. Then, if you heat them in air, they would burn. But if you remove air and you would go to nitrogen or argon, in that case, you start really getting a kind of a fusion of these leathers, and then you get a graphitic structure. But what is very interesting is that nitrogen will be still present at these edges. So they are more or less like a pyridinic nitrogens. So you will have a, depending now on the size of morphology and so on, you may have a sometimes very large surface area with exposed nitrogen atoms at the edges. So this happens at around 500 degrees. And then if you heat more and more and more, they will be fused more and more and more. You go to 2000 degrees, nitrogen is gone completely. So this would be a way to make a graphitic fibers. But we are interested in preserving nitrogen. So this would be important how to do that. So let me start really with synthesis of polyacrylonitrile, because if you want to make a block of polymers, you need to have a well-defined structures. So this is an example of one of the first really well-defined polyacrylonitrile. You could see from MALDI time of flight, dispersity is 1.01. So we can make really extremely well-defined structures. And this was, in fact, one of the first examples of using ATRP in polyacrylonitrile. We use classical system, as you heard on my second lecture, copper bromide BP and typically 2-bromopropionitrile. Everything works in a very nice way. These were relatively low molar mass systems and high copper loading, so this amount of copper was in a range of 1,000 ppm or more. And if you want to go to higher molecular weight, now we can use these low ppm copper systems. And this is based on this much stronger ligand, this 3-spiridyl methylamine, and we use as a reducing agent, in that case, tin, sometimes glucose, some other systems as well. And you could see that we can reach molar masses in a range of 100,000 or sometimes even more. And this system works quite nicely. So what other techniques we can use? One example is ICAR. ICAR, as you remember from my second lecture, is a process when we use AIBN as a reducing agent or as a constant supply of radicals to compensate for radical termination. And the best systems are based on initiators, which is bromopropionitrile, mimicking essentially structure of polyacrylonitrile, or even more active ethyl bromophenylacetate and ligands TPMA. You could see dispersed to 1.1, so it works very, very nicely. So what will happen if I will be reducing progressively the amount of copper? This was at the end of my second lecture, really telling you that if I go to lower and lower amount of copper, in fact, I may have a still control of molecular weight, but you have a broader and broader molecular weight distribution because exchange reactions would not happen efficiently. And indeed, you could see here what happens if I go with a 50, 25, 10 ppm, molar masses are nicely controlled. 1 ppm, they increase, but there is a kind of a jump at the beginning. I don't have enough copper to control all of them, but because of that, I can also control molecular weight distribution. And this may have a very interesting implication for morphologies, going to some kind of a bicontinuous morphologies as well. Another approach would be to use, instead of the AIBN or tin compound, I can use copper zero. So copper zero is essentially plugging in copper wire to a system, and again, good control of molar masses, dispersities in a range of 1.2 or 1.1 sometimes. And copper is a piece of copper wire 1 millimeter diameter, 3 centimeter length essentially, which you can remove later from the reaction mixture. Now, can I remove completely copper from a system? So this is an example of using metal-free ATRP, and we are using phenylthiazine as a phenylthiazine redox photoinitiator or photocatalyst. And again, dispersity is probably not as good in a range of 1.5. Molar masses start high, but eventually they just merge to these theoretical values. So you can work nearly without any kind of here, without any transition metal left in a system. Other techniques of polymerizing acrylonitrile is a classical raft process. So in that case, we are using dithiol esters. In fact, it's an acrylonitrile-based system, and then they can exchange progressively. Molar masses increase, dispersities in a range of 1.1, and the same can be done with nitroxide. Typically, we use this SG1, which is a commercial material available from Arkema recently, and again, pretty good control of molar masses and distributions. Now, there is another interesting possibility that I told you. Polyacrylonitrile is soluble essentially in DMF, DMSO, ethylene carbonate, but also in a very highly concentrated solution of isocyanate. Sodium isocyanate, 50 weight percent, dissolves polyacrylonitrile. In fact, it is used commercially to make polyacrylonitrile fibers. So we recently submitted a paper. How to do that? We go to this 50 weight percent of sodium isocyanate or thiocyanate, and then you can still have a good control of molar masses and relatively low dispersity using quite unusual solvents. So polyacrylonitrile from this point of view is unique polymer, you may say. Now, how we can make block copolymers? Because you would like to have this porosity defined by block copolymer structure. So usually for block copolymerization, which I told you at the last lecture, you must start from a more active monomer first, and then at second monomer, which would be less active. So for example, if I start with polybutyl acrylate and add acrylonitrile, which is a bad choice, in a sense that once I would switch one of these, they would propagate very fast and some other chains will not be initiated. So this is not a good way. The better way is to start with polyacrylonitrile and add butyl acrylate, and now all of these chains would start growing progressively. However, if you use ATRP, you have one other possibility. You can have so-called halogen exchange, because reactivity is, in fact, reactivity of a chain end, bromine versus chlorine, and reactivity of acrylate versus acrylonitrile. So in fact, what happens that acrylonitrile is much more active, so chain end would grow faster than butyl acrylate, but also bromine is much more active than chlorine. So if I would start with a bromoacrylate, I can add copper chloride, have a halogen exchange, and now reactivity of this bromoacrylate matches reactivity of chloroacrylonitrile. And now all of these chains continue to grow at the same time. There is, however, one problem, that in that case you need to have enough chlorine source, or copper, which would match amount of the bromine. So you have to put 1-to-1, essentially, copper chloride. So if you don't want to do that, in fact, you can go with acrylonitrile and go with acrylate first. There is, however, a small problem because of solubility. If you would add butyl acrylate, non-polar solvent, to solution of polyacrylonitrile in, for example, DMSO, DMF, you precipitate polyacrylonitrile. So you have to add it slowly, progressively, because otherwise, if you add it at once, you will precipitate polyacrylonitrile. So having some of these tricks, you essentially can end up with this one-pot process by slow addition of polybutyl acrylate. Dispersed is very good. Everything works in a nice way. So we know how to polymerize acrylonitrile. We know how to make block copolymers. So what do we do with them? So in fact, having diblocks or triblocks, you can start with a difunctional sometimes structure, getting triblock copolymers. You can phase separate them into different morphologies, into spheres, into cylinders, into lamellae, and then we can, by zone casting, really order them in a nice way. If you have a drop casting, there would be separation of the different block copolymers regions concurrently, so you not have a macroscopic order in contrast to this zone casting process. I showed you before also that we can do something similar with cylinders. These are filaments of 30 nanometers diameter. This scale bar here, or size of this TM is 3 microns, so they are 30 nanometers diameter. And they are very different than classical carbon fibers, which are 50 microns. So if you take a 50 micron fiber and taking 1 gram or 1 cubic centimeter of it, one single cylinder would correspond to 500 meters length. And if you go to 30 nanometers, they would be, roughly speaking, 2,000 by 2,000 times longer. So it would be 1.5 million kilometers of an individual filament. So, of course, it's a very large surface to volume ratio, very important for making nanocomposites, for dispersing them in various type of matrices. So I showed you lamellae, I showed you cylinders, but probably the most interesting may be bicontinuous structure. So this bicontinuous structure depends on the volume fraction, depends also to some degree on a dispersity of both blocks. This would be around 42% of polyacrylonitrile. Very large surface area still preserved, 500 square meters per gram. From a small angle X-ray, you could see a period 23 nanometers, and from the nitrogen sorption, 13 nanometers pore size. So it means that what I have a 10 nanometer, essentially interconnected structure. So it's a polyacrylonitrile, eventually with these nitrogen atoms at the edges of the carbon wall of a thickness of only 10 nanometers. So to do that, you need, of course, to still control porosity. You need to control morphology. We start with polyacrylonitrile, 280 degrees in air, cross-linking, 500 to 1,000 degrees. We can carbonize them, and we can control morphologies, which is important, especially for some electro-related application, for supercapacitors, for oxygen reduction, for hydrogen evolution reaction, but also for CO2 sorption and some others. So porosity, in fact, has maybe two origins. One, porosity is really micropores below 2 nanometers, which is very inherently connected to polyacrylonitrile alone. And it doesn't matter really what kind of polyacrylonitrile you have if you do not collapse this structure in the right way. And the other one, mesoporous porosity of a larger diameter, they are really dialed by the block copolymer, by the sacrificial block polybutyl acrylate. And we can have it in a range of sometimes between maybe 5 to 20 nanometers. Depends what size of this second block you will have. So if you have a polyacrylonitrile alone, the mesoporous values are pretty small, but for any kind of a block of polymers, they are preserved, and because of that, you have a totally much larger total volume size. Now, there are really two issues. One is that if I would go to potentially high and higher temperatures, so this is graphitization at 600, 700, 800, 900, 1,000 degrees, in principle, I will have a more and more conductive material because I will have a better, essentially, connectivity and less defects in the system. But I would lose really proportion of nitrogen. So I start from something like 17%, I go to 5%. So there is a kind of a compromise because I would like to have a sufficiently conductive material with a good porosity, but also with a sufficiently high nitrogen content, especially for catalytic purpose. There are several types of nitrogen. So this would be these pyridinic nitrogens. This would be also pyridine oxide, pyrrolic structure, and sometimes also quaternary ammonium structures as well. So I will try now to switch a little bit to this application of polyacrylonitrile-based nanocarbons, and I will give you some examples what can be done with CO2 capture what can be done with these electroactive systems and also supercapacitors and some others. So we always would start with block copolymers or with the porous structure, which would be inherently related to the hard templating system, but especially for block copolymers. So let me start with the CO2 capture and CO2 reduction in principle. It's a really big problem what happens with CO2. The amount of CO2 during the last essentially century after Industrial Revolution explosively increased from values which were around 280 parts per million to nearly 400 parts per million now. And because of that, there are really many issues. One is the increase of the temperature, and because of that also melting of the icebergs, and because of that level of water increase in 20th century by 18 centimeters. Projection is that by the end of 21st century, maybe 50 centimeters higher. If you look at the pH, also pH significantly dropped down from 8.18 to approximately 8.07, so this is of course logarithmic scale. So there are several components, what happens and why it happens. In fact, industry does not contribute that much. It's only 20% of CO2 production. Mostly it is transport and electricity and heat, and essentially we have this Pandora box open and CO2 is going out. So can we return it? And there are really two approaches how we can capture it. We can capture it by using various highly porous structures and sometimes with functionalities. So this would be amine scrubbing, but also zeolites, sometimes carbon, calcium oxide, activated carbons, ionic liquids, and some others. So there are two approaches how one can do that. One, this evil, which we essentially produce, we can send it to hell, which means underground, and this can be a capture process. And the other one, we can turn it into an angel, potentially reuse the CO2 and make some biomass, enhance oil recovery, and some others. So we try to do that in two ways. One is by capture and storage, and this would include some resins, but also using these carbons, which I mentioned to you before. These are nanocarbons with pyridinic nitrogens, which has affinity to CO2. And this would depend on the pressure, would depend also on temperature. And the other one is catalytic conversion based on the essentially producing methanol, methane, but also formic acid and some others as well. So here is one example. When you start with these carbons, they are, as I showed you before, they have a moderate surface area in a range of 500 square meters per gram. And if you look at the activated carbons without any nitrogens, it has a larger surface area, but capacity is essentially smaller. So here, although surface area is smaller, the sorption, like in that case, is 2.7 versus 2, which is really exceeding classical activated carbons. And also selectivity, this is absorption of CO2 versus nitrogen is in a range of a factor of 20 or 30. So can we use also these nanocarbons for some other purpose? This is a classical oxygen reduction process. And we would like to replace expensive platinum electrode with nanocarbons. This is a classical carbon nanotubes. This is platinum, and this is this nitrogen-doped carbon templated materials. So this is processing by 4-electron system, and they are essentially as efficient as platinum under these conditions. The efficiency depends on also conditions you make these nanocarbons. So you have this temperature of pyrolysis in which if you go to higher and higher temperature, nitrogen content will be progressively decreasing, but electrical conductivity would increase. And you need to find a compromise. Because if you would go to too low values, in that case, you have a really current versus pyrolysis temperature, 600 because of poor conductivity, it doesn't work. you go to 700, 800, but if you go to too high temperature, nitrogen content drops and they are less efficient. So something between 700 and 800 temperature is really optimal. And here is the same comparison. So this is the platinum. This is 700 temperature film. And if you go to the pure polyacrylonitrile, it works in a much less efficient way. One advantage of these materials is that you do not need to use any kind of a filler. There is practically no filler in it, so you can make a drop of block copolymer solution and then deposit it on the, in that case, glassy carbon electrode, and develop this bicontinuous structure directly on a system, so it has a high porosity and high performance. Hydrogen evolution reaction is another important issue for water splitting and some other applications. And so far, platinum is by far the best system. So can we use this nitrogen-doped carbon in a similar application as platinum? And originally, we were extremely excited about it, but less excited after some time. So if you look here, what happens with a classical platinum electrode, if you deposit that, or your counter electrode is glassy carbon, if I have a glassy carbon in a presence of these copolymer templated nanocarbons, this is 600, 700, 800. They are much better, of course, than glassy carbon, but then still not matching the platinum. However, if you use a platinum electrode, in that case, these nanocarbons practically behaves like a platinum. So what happens, you have a very small amount of a platinum deposited on this nanocarbon, and you can measure that the amount of platinum is in a range of probably 0.01%. So it is not 100% platinum, but still platinum acts on a surface. And you can see it, depending on temperature, the size of these platinum clusters are still there. But you can match this platinum electrode with the platinum deposited on carbon through various cycles, and essentially electrochemically they are nearly equivalent, although content of platinum is very small. So let me switch now to some issues related to bioconjugates. So bioconjugates, like covalently linking organic and inorganic materials, it is covalently linking natural and synthetic polymers. So there are a couple ways how to do that. We can make either coupling of a polymer chains with the protein or with enzyme, or we can grow one by one monomer unit and get these hybrid materials. I will show you some examples of that, but also some example of using nucleic acids by using phosphoramidate chemistry, and this would be essentially two. I showed you in a first lecture example of making polyplexes and deliver it of sRNA under these conditions. So there are two ways, as I mentioned to you, how to make protein polymer hybrids. One example is to take a polymer which would have a functional group complementary to something which is on the surface of a protein or enzyme. It can be typically amino group or thiol groups, and in that case you can react them with an end functional structure. But because we work under very high dilution, one needs to use very large excess of a polymer, factor of 10 or 20, and then to separate them is not easy, especially if molar mass of this biomolecule and the polymer are similar. So another approach is really to grow one by one using functionalized structure, and one can have a pegylated polymers, thermoresponsive, just pH responsive, and some others as well. So this has been done in literature before with a moderate success. So here are two examples of having polymer with a disulfide linker. This is work by Heather Maynard, and then growing the smart polynipam polymer from it. It works, but if you look here, this is the initial starting material. This is a bioconjugate. There is still something left unreacted, and a big tailing. If you go to another work by Tosh Chilcotti, It's a polymer which would be grown by ATRP in that case, and you have the same initial material and the bioconjugate, still a lot of left, and the tailing here as well. We used something similar by a biotechnological approach, more or less. It was work done together with Ryan Mell. He incorporated position 134, this ATRP bromoamide. And polymerization works. If you look at the gel, everything moves towards higher molecular weight, but still there is something unreacted here and the tailing. So it has to be somehow improved. Maybe first the question is, what is a challenge? If you want to make under biorelevant conditions, it means that we work in water, in a buffer. Content of water would be 80–90%. The rest is a monomer, because you have to have a monomer, 10–20%. You need to work under highly dilute conditions in order to prevent any kind of a protein aggregation, and also at ambient temperature to prevent denaturation of a protein. So these are initial conditions which are a little bit challenging. But if you work in water, this ATRP equilibrium has various special aspects. One, what I told you already at the second lecture, that equilibrium constant in water for ATRP is very large. It is 10,000 times larger than in acetonitrile. So if you would apply the same conditions, you will flood the system with radicals. They will terminate one with another. There would be no control. Another issue is that these species, copper-2 with a halogen, in water can dissociate. And now you have also copper-2 species without halogen, so radicals cannot react with it. So in that case, we add sometimes excess of halogen in order to shift this equilibrium by Le Chatelier principle to the same deactivating species. You can sometimes hydrolyze these bonds. You can also have disproportionation. So all of that has to be taken into account. So I will show you one example how you can approach a system. So we take two more expensive, less expensive model studies. We work in water with a water-soluble monomer, and we use two different initiators, more active, less active. And either we use polyethylene oxide-based macroinitiator, or we take this BSA protein with roughly 30 initiating units, as can be measured by mass spec. So then, after applying this polymerization, we can grow a chain and then digest a protein, and in that case, we can analyze polymers and see how they work. So there will be two systems. One system will be based on the normal so-called ATRP, and we are using, in this case, bipyridine, this originally used system. And the other one would be at a much lower concentration of copper using trispyridine methylamine. This one is 3,000 times more active than this one. Additional trick, as I mentioned to you before, is halogens make a difference. Bromine is approximately 15 times more active than chlorine. So in a normal ATRP, we use enough amount of copper-1, but because it's so active system, we use a lot of copper-2 also, so small amount of copper-1. In a second approach, we start only with copper-2, but this copper-2 will be reduced in situ using this ascorbic acid as a reducing agent. So you start only with copper-2, you don't worry about any oxygen, then you add a little bit of ascorbic acid and polymerization should start. So how does it work? So we compare really two different systems. One is this bipyridyl, which is not very active, and the other one, trispyridyl methylamine, which is very active. We start with 90% copper-2, only 10% of copper-1. In organic solvent, it would not work at all. It would be so much copper-2 that reaction would take weeks, essentially, to complete. And here what happens, this one, which is less active, this copper BP, goes very nicely to 90% conversion or so. And this, which is very active, this TPMA, practically 5% conversion, which is totally opposite to expectations. But if you look really what happens, in fact, this system, this TPMA, works at a very low conversion and reaction stops, which means most likely it is a too active reaction. We have this 10% is way too much. So can we use, instead of 10%, can we use just 0.3% only copper-1? And now what you could see that it goes and stops, goes and stops. So I can add this reducing agent, in that case I add ascorbic acid, in a very small amount, and it can grow. But can I do it continuously? And if I do it continuously, reaction now starts working in a beautiful way. Rate of the addition is very small. It is 8 nanomole per minute. So using syringe pump, I essentially feed ascorbic acid solution to the system, and you could see that conversion goes very nicely. Molar masses increase and dispersity stayed very low, like 1.16 or so. So this was done for a model system. You can do the same, in fact, with this protein. For protein, we are using PBS buffer. And PBS buffer gives you one advantage also, that it contains corresponding halide anions, bromine or chlorine. And in that case, you could see that polymerization works in an efficient way. Molar masses increase with conversion, and dispersity stayed very low. So you are using, in that case, a little bit of the ascorbic acid progressively added to the system. So to summarize, how could I recommend you to run this polymerization? There are two ways. One way is that you can use normal ATRP. In that case, you can use this less active ligand BP, 10% of copper 1, 90% of copper 2. But another option is that you use this much more active ligand, 3-spiryl-methylamine, and then you feed very slowly ascorbic acid to the system, essentially feeding dropwise, and polymerization works in an efficient way. So the last thing which I wanted to finish it is really synthesis of the nucleic acid-based system. It's a little bit more challenging than first because it's much more expensive than proteins. So you have to work in a small amount, sometimes really micrograms nearly of a polymer. We use a concept very similar as is used in DNA synthesis. We prepared phosphoramidite, which contains this ATRP amide, which can be added at whatever moment of the DNA synthesis. Sometimes at the end to make a block copolymer, sometimes in the middle to make a graft copolymer or several graft copolymers. So the way it is done is typically using this control porosity glass. We grow the DNA to whatever length and whatever sequence we want. Then we add this phosphoramidite, then we cleave it, and we start looking at the polymerization. Amount of a polymer is, as I mentioned to you, micrograms to start with. So in order to observe everything, we can use copolymer, which could contain also a dye, so you can see really this dye incorporated to the polymer chains. And in fact, these are probably the smallest scale reaction we have ever done. So you could see that this volume is approximately 200 microliters. So it's essentially a drop of solution. Color comes from rhodamine containing metacrylates. However, if you could see really at the polymerization, maybe I can show you even GPC traces. So you could see that this, starting from this macro initiator, we go to one or another system. Molar masses are in a range of 200,000, and dispersity is 1.2, 1.3. This is 60,000, 1.3 as well. So you can really control it. But one system which I wanted to show you is in fact the conjugate between the polymer and protein through the DNA. So in that case, by clicking this protein, this is a green fluorescent protein, with one type of DNA, we get the conjugate, and then we make another polymer with a complementary DNA, which can connect together one to another. And of course, at higher temperature, they can melt, dissociate, or you can displace them by adding excess of another DNA, but by thread, you can see really that they are together. So this is an example of a bioconjugate between protein and polymer via DNA coupling system. So the very last issue is probably coming back to the catalysis. Normally, we use systems which are not bio-based, but there is a recent development of so-called ATRP ASEs, and this was started by my former postdoc Fabio Di Lena and also by Nico Bruns at Basel. So they, instead of using a redox system based on the ascorbic acid or electrochemistry or something else, they found that in fact you can use some kind of a heme-based system, which are also redox active, and they will have a certain affinity towards bromine, and they can act as the catalyst for atom transfer radical polymerization. This is based on horseradish peroxidase, sometimes can be just on various type of hemines, as you will see also some other systems as well. Polymerization starts and then stops. You could see that this molar mass distribution is pretty broad, not very good control, and essentially you go to limited conversion. One of the interesting extension was done by Nico Bruns, and he was brave enough to take his own blood and the erythrocytes, which catalyzed ATRP. I'm not sure if it is illegal in France, but in Switzerland they had no problems with it. At least he published a paper. So it is essentially, as you could see, his last name when he took his blood. The amount was, of course, not very large. So in that case, you could use the NIPAM system, and if you go to higher temperature, everything precipitates. You go to lower temperature, it starts to dissolve. However, can you go in a simple way? And in fact, it's called a catalyst, but some of these catalysts, they have a molar mass 50,000. If you want to make a polymer 50,000 molecular weight, it is essentially 1-to-1 polymer versus catalyst. So can we shave more or less all of this part, a protein, and can we focus only on the hemine in this particular case? And if you start working with hemine, solubility is not very good, so we extended it first with a pegylated structures and sometimes with a functional structures as well. And it worked very nicely, in fact. However, you got beautifully red polymers. Because these double bonds here, they can get incorporated into polymer chains. So you get a polymethyl methacrylate with a beautiful red color. After reduction, after hydrogenation, they cannot be incorporated. And what you get is, in that case, polymers with a good control of molar masses, dispersities in a range of 1.2. So they are more bio-inspired, in some sense, catalysts. And in fact, they can be used also for methacrylic acid quite efficiently. And then what would be next step is really to incorporate thiol groups, which can complex, and also imidazole groups, which would be really more bio-mimicking. So with that, I think I am coming to the end. And I would like to really tell you that in more or less all what I told you is that we want to make certain materials, certain polymers, whether it would be bio-related, sometimes maybe energy-related, sometimes maybe environmental-related, some advanced materials, super soft structures, gels, which can evolve in a different way. And you start really with the idea why to do something. And then you try to translate it to the structure which you can draw on a paper. Essentially, what would be a topology? What would be composition? What would be a functionality? And how you can really control this polymerization would be a next step. Of course, you have to control it every moment. Then we need to have sometimes controlled processing, because morphologies would depend sometimes on solvent, on thermal history, on some mechanical stresses. And then you can see whether you are getting these structures in a proper way. So more or less all of this macromolecular engineering starts with this rational design through synthesis, processing to get these final material properties. However, this may be good for a cover in a nice paper. If you want to make 1,000 of tons of these materials, you need to make also very good cost-performance analysis. And sometimes these materials may be too sophisticated. They may have an unnecessarily narrow molecular weight distribution. So can we make them, for example, making a star with 5 arms? 4 would be enough, or maybe 3 would be enough, or maybe 6. So can I have a broader distribution of these structures? Can I sometimes have a broader molecular weight distribution of a polymer and maybe even end up with a various special morphologies, which, as I showed you, these hexagonally perforated lamellae. So these are things which sometimes unexpected, and maybe this molecular weight distribution will become a next parameter for tuning different material properties and different behavior. So with that, I would like to acknowledge again my team at Carnegie Mellon and thank Clément for invitation. I spent beautiful 4 weeks in Paris, sometimes with umbrella, but it was really a very enjoyable stay, and thank you very much for coming in spite of weather here. So I will be glad to answer any questions if you have. Thank you.